In this problem, we're looking at a textbook that's sitting on the seat of a car, and somebody's driving along, and the book is not sliding relative to the seat. So the book is in motion, but it's not sliding. Once the speed of the car gets to 14 meters per second, that's when the book begins to slide. And we're supposed to determine the coefficient of static friction between the book and the seat. So before we get into a solution, we're going to outline what our steps would be in this solution. So first thing would be to determine what object are we interested in. So what is the object or system of interest? And in this case, it would be the book. Next, we want to draw a free body diagram of the book, and we need to think about what perspective we want to use. So we could do a top view, or a side view, or a rear view, and I think the rear view is going to be the best bet, and we'll see how that works out on the next slide. We're going to choose a coordinate system, and since the book is moving in a curved path, we're going to make sure we have an R direction. There will be a T direction, and we'll have to decide whether there is a Y direction or not. We're going to sum the forces in the Y direction. Okay, I just gave that away. We are going to have a Y direction. And the reason we already know that we're going to have a Y direction is because the object of interest, the book, is not changing height throughout the process. So whenever the height of the object stays the same throughout the whole process as it's going in the curved path, then you are going to have a Y direction. We're going to sum the forces in the R direction. We're going to use the equation for the maximum static friction, and it is static friction because we're interested in that moment just before the book begins to slide. And we're going to put those three equations together to find the coefficient of static friction. Alright, so here we go. I've already labeled my free body diagram as being for a rear view. And we're using Chapter 4 and Chapter 6 and Chapter 5. Forgot about that. This problem really puts everything together. We're going to be finding mu sub s, which is always a positive value, and it has no units. We also know it's between 0 and 1. And so just to give some perspective, I did want to just look at this top view for a moment. And so the car is going round and round, the book is going round and round, but let's say it's at this moment where the book is right there. And then we are standing right here. So the car is headed, the book and the car are headed around this way. Okay. And we're watching, and the book is going away from us and turning left. Okay. So that's our top view. But now, when we draw a free body diagram, we're looking at it from the rear view. So, since we're looking from the rear view, we know there's a normal force acting up. Oh, and by the way, since we're standing back here, we also have to imagine that we have X-ray vision, and we're looking in at the book from all the way when it's in the car. So, we also know that there's weight pulling straight down. And then, well, let's think about the coordinate systems that we're using here. This is going to be our Y direction. And which way is the R direction? Well, if we're standing here looking at it, the center of the circle is here, so the R direction is to the left. So this is our positive R direction over here. And so we know there has to be a force in the positive R direction. So even before we know what that force is, we know there has to be one. And we think about it and we think, okay, what's making that book turn left? Well, it's because it's in contact with the seat and because of the friction. Another clue in this particular problem is that we're asked to find the coefficient of static friction, so that makes it a little bit easier to know that there's static friction acting in this case. Alright, so now we're going to proceed with our plan, which is to use these three equations here. So we'll go ahead and do this one. So we have normal force minus weight equals MAY, and the book is not changing height throughout the entire time, so it has zero acceleration in the Y direction. In the R direction, it's quite simple. we have Fs, and that's it, equals MAC, which is also equal to mv squared over r. And then we have this equation, Fs max equals mu s Fn. All right, so let's think about what we know and we don't know in this equation. We don't know what the normal force is, and we don't know what the weight is, and we don't know what the static friction is. We do know V, we do know R, and let's see, we don't know the static friction, and we don't know that, and we don't know that. So that's a whole lot of unknowns. So we need to try to put these together to try to make this work out. It looks like we don't have enough information. We're always going to try to keep going as much as we can. So we're going to take this, we're going to substitute it in there. We can solve this equation, say that Fn equals W. So we're going to take this value, substitute it in right there, and I'm just going to pop down here. So we get M V squared over R equals mu S times W. But we know that W equals what? Mg. So now we can substitute this in right here. We say mv squared over R equals mu S times mg. And now we see we can divide both sides by m, and we can divide both sides by g. Okay, so that cancels, that cancels. So mu S equals v squared over gr, which is equal to 14 meters per second squared divided by 9.8. Meters per second squared times the radius, which was given on the last page, and then the problem, times 50. Now we'll calculate this. 14 squared divided by 9.8 divided by 50, 0.4. So I kind of ran out of room there. I'll just put an arrow. I understand that sometimes your solutions are not always going to fit in a nice pattern, but if you just use some arrows, it really helps the person reading it to understand what's going on. Alright, is the solution complete? Well, let's go back to our other page here, and it says that we are supposed to find the coefficient of static friction. So we did that. Alright, so our solution is complete. Is the sign of the answer correct? Yeah, we had positive, 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 and our answer came out positive, and that's what we expected. Does it have the correct units? Ooh, alright, so let's look here. We've got meters per second. I'm just going to analyze this right here. Meters per second squared divided by meters per second squared times meters. So if we look here in the top, we're going to have meters squared per second squared, and then in the numerator, in the denominator, we're also going to have meters squared per second squared. So that's going to come out to no units, and that's exactly what we expected. It's dimensionless. So that's correct. Is the magnitude of the answer reasonable? Yes, it is. 0.4 is a number between 0 and 1, which is what almost all coefficients of friction are. You can occasionally have one that's a little bit above 1, but almost always between 0 and 1. All right. All finished.